Okay, we had a bit of a malfunction there with my gateway. Oops, that's not the one I wanted to open. Okay. I saw this thing, and fuck did it ever piss me off. Any quick? I'm retarded. Come on back. But no, this really fucking pissed me off when I read it. eChat got hacked. Yeah, that'll happen. There's a thing in the past couple of days talking about summing prime numbers up to X number of digits. Bubble sort in Lisp. I think the post turned into vapor. Or maybe I got confused and just thought something existed where it did not. This one kind of got my blood going too. So this fucking idiot asked, when will 128-bit technology be in the works? Okay, you're asking for a 128-bit CPU, and you don't even fucking know. It can't fucking exist. Never will fucking exist. Ever. Okay, not in this lifetime, not in my lifetime, not in your kid's timeline, not in your grandkids' timeline. Ever. We're talking about word length and memory addressing. Once you start going 128-bit, we're talking about a computer that can address more memory than there are stars in this galaxy. Okay? It just can't be done. Like, what the fuck do you want out of it? You know? Now I can't even find the post. AMD is dying. It's literally dead. Well, the thing was, it was, um, it was a stream. There was a bunch of posts of people. How do you calculate prime numbers? Oops, I done goofed. Calculating the sums of prime numbers. How to do that? And I may have been wrong, but I'm fairly sure that I read somewhere that a guy was able to compute the sums of prime numbers up to, you know, 1 million, 2 million, you know, whatever amount. And he was proud of himself for doing it in 1,000 lines of code. I sat there thinking, buddy, are you fucking kidding me? Okay, now check this out. I wrote it in C. Okay. In 44 lines of code. And, you know, I'm not the best programmer in the world. Far from it. But, you know, I can compute sums of prime numbers in less than 1,000 lines. You know, anybody with half a brain can do that. So I'll go ahead and compile this. Where am I here? Okay, so what this program will do is it'll calculate all the prime numbers. It will find all prime numbers between 1 and a number that you give it, and it will add them all together. So the sum of all the primes between 1 and, say, 10,000 or 100,000. Sum of all prime numbers is 454,396,537. And I did that in 44 lines of code. Not fucking 1,000. you want to talk? Great programmers. I always forget his name. Anders Hellsberg. He wrote the Borland. Well, back then he worked for Borland, and he wrote the C++ compiler and 32 kilobytes. Okay. But now he works at Microsoft, and he created the C# language.
C. I come from a long background of programming in Pascal and Delphi and whatever, lots of influences there, like, Delphi had properties and C# has properties, and it's because I think properties are a good thing. So it's nothing gets designed in a vacuum, and we all stand on the shoulders of giants, et cetera, et cetera. It's every programming language builds on what went before it. That's the prudent and right way to do development. So there was a multitude of inspiration.
Absolutely. Which is true for, like you said, for Java as well.
Oh yeah, absolutely. Java was hugely influenced by Smalltalk, for example, and C++ obviously, and C. And honestly, there will be languages after Java and after C# that will be influenced by both of those, and take the good parts and dump the bad, and add a little bit. That's sort of how you design new stuff, right? You take the core and then you lop off a little bit and you pepper on some new stuff, and there it is.
Well, that brings up an excellent question. How do you design a programming language? Do you start with the compiler, or do you?
No, C# was not designed by starting with a compiler. Because the compiler is the embodiment of the language, if you will, but it is not the language, right? It is just a translator of the language to some other form. Of course, you want to think about whether it is possible to compile this language and whether it can be efficient and so forth. But once you establish that, I think the compiler is really something that is best viewed as a separate piece. So we designed the language as an entity by itself. We wrote a language specification and so forth. If I had to say, the one thing about language design is the hard part is not what to put in. The hard part is what to keep out, right? There are lots of things you could put in, lots of crazy ideas, but how do you make sure that it doesn't look like a kitchen sink, right? And how do you make sure that there's some sort of guiding principle and once I learn about this sort of seems familiar over here automatically, and how do you establish a philosophy of the language that just sort of naturally, when you know this feature, this other feature feels right in the same context, right? And it's very much subjective, and it's very much about having good taste, whatever that means. It's not something that you can just sort of like pick up a book and do. I think because it is ultimately an embodiment of what we think is the right way to program, right? But it's just our view of it, the design group. It's not the only one right view.
the three best compilers in the world right now are LLVM, that's produced by Apple. Its suite of cross compiler tools and all the languages it manages. So you have C, C++, cross compiling to different CPU architectures. You have ICC, that is the Intel compiler collection. So you have C, C++, and Fortran, and Microsoft's Visual Studio and its languages, Visual Basic, C++, and C#. Pascal, oh geez, I remember that language. Anything recent? Check this out.
Hi, I'm David Bolton of Go Parallel, and today I'm going to be looking at what's new in the Intel C++ compiler that comes with Intel Parallel Studio XE 2016. So far there's been an initial release, followed by incremental changes in 2 updates. These changes can be summed up as A. For the Intel Many Integrated Core Architecture, B. Adding support for Intel graphics technology, C. Adding multi-threading support for Intel TBB, OpenMP 4.0, and Intel Sub Plus, and D. Adding more C11 and C++ 14 features. Let's look at these changes seen with Intel Many Integrated Core Architecture, or Intel MIC for short. This has been an ongoing project for almost 9 years. Its aim is to provide a lot more power through multiprocessing and head towards exaflop processing speeds. Earlier incarnations of Intel MIC were provided with Knight's Corner, Knight's Landing, and Knight's Hill product lines, but it's now called Xeon Phi. By supporting Intel TBB, Intel Silk, and OpenMP, the intention is that existing code can be recompiled with barely a change of code. New changes include the ability to offload computations to Intel MIC in single or multiple streams. This is done through pragmas to define the offloads. Many Intel processors include Intel graphics technology. This can be used to do computations with a minimal amount of code. The compiler generates code that runs on the host and also code that is offloaded to the graphics processor. Changes in the compiler include an API that lets you query hardware information. You can retrieve info about the platform, including thread count and device, min, max, and current frequencies. In addition, your software can control thread group space, including width and height at runtime. This tells it how many threads are in a group and how many groups there are. There's also shared local support for click-for loops. This can help reduce RAM usage and improve performance. There's a new compiler option that helps protect parentheses and prevents the optimizer doing something unexpected. Normally, optimizers will rearrange calculations for optimal performance, but there may be rare occasions when the order of operations is more important. For example, because of rounding, and this option will let you do that. The downside is that it may make your code run slower because it's not optimized. One thing to bear in mind is that the Linux version of Intel C++ compiler is slightly more feature complete than the Windows version. The previous version of the compiler fully supported C++ 11, except for a few features that are only implemented on the Linux and OS X versions. The new compiler has some support for C++ 14, and this has to be enabled with the compiler option /q standard equals C++ 14. Likewise for C11/q standard equals C11. I tried out with the Visual C++ version, and compilation is fast. As there was a beta, there were 1 or 2 minor gotchas, but you expect that. Other changes include an implementation of the decimal type on Windows. While this is already in the Linux and OS X compiler, and provide 32, 64, and 128-bit decimal arithmetic as defined in the IEEE standard 754-2008. There are newer versions of Intel's math kernel library, Intel MemKL, and Intel Integrated Performance Primitives, Intel IPP. The math kernel libraries added MPI wrappers to support custom MPIs such as Cray MPI and IBM MPI, and the Intel IPP adds IVX 512 optimization. In conclusion, I describe the release of version 16 of the Intel C++ compiler as evolutionary rather than revolutionary. Thank you for watching this video. I'm David Bolton of GoParrot.
Hi, I'm Jeff Cogswell, and today we're going to talk about how to get the compiler to generate vectorized code, and we're going to take a look at the assembler code and make sure that it really is vectorized. So I've got here some C++ code. Basically, I'm creating 3 arrays. Each is holding a float, and each one holds 128 floats. And then I'm initializing these arrays. I'm just putting some random numbers basically, because I mean they're not random, but I'm just test data inside each of them. A is going to hold I over 10, and B is going to hold I over 20, and I'm initializing C to 0. Now technically, I don't really need to initialize C to 0. The compiler does automatically put zeros in it for us, and Intel has verified that for us. However, it's just good programming practice, just in case we ever decide to port this to other compilers where that might not be a guarantee. And then I'm going to look through these, and here's where my vectorization is taking place. I'm doing just a simple addition here. Now, we have, of course, many different operations we can do, but for now we're just going to look at the addition just because it's a little bit easier. And then finally, I'm just going to print out what I've got. So let's go over here to the compiler. Now, instead of using Visual Studio right now, I'm using the Intel command line compiler. So I need to go over to the Intel directory. And it's in the composer and in the bin. And in here are some scripts that will set up the compiler variables for us. The one we want is the ICL vars.bat. I'm just going to paste that in and run it, and it'll give you the command line options. And it's going to tell us the one we want is Intel 64. That's going to set up Intel 64 for both host and target. So we put Intel 64 here. And now we're set up to use the compiler. Let's go back to my tests here. Okay, now I've got the code here. I'm going to go ahead and delete the object file and executable, since I had already tested this earlier. Now, the ICL is the command line, and we can just do test1.cpp. It'll compile it, but it won't really give us any information about what happened. So let's turn on the vectorization report. Now, it's doing auto vectorization, but we don't know that. So we do qvec report 2, then it'll report back to us the vectorization. Now, there's a whole bunch because it's also digging down into the include files and telling us that those aren't vectorized. Let's scroll up, and right there we see loop was vectorized, loop was vectorized. That happened on line 11 and line 17. So let's go ahead and look at those. Turn on the line numbers here. Line 11 is this loop where I'm initializing it, and line 17 is where I'm doing my actual work. So it actually vectorized when I was just initializing the arrays, and that's good too. Our main focus here is in this one right here. Now let's go ahead and look at the assembler output. Oh, before we do this, I want to also, by default, it doesn't generate AVX code. It's for an earlier SIMD. So let's add in another option here. Let's do QX, and for AVX we do core-AVX-I. Let's run it again. And now we should have AVX code. But we want to actually look at it, and for that we're going to need a compiler option. So let's look at that for a second. To see the assembly code, we add the /s option. So let's go ahead and add that. And now we've got a .asm file. Let's open that up. Okay, so here's the code, and it's actually line 18 because that's where the vectorized line was. And the V here means we've targeted the AVX processor, and the first operation is a move, and the P here means pack, and that's the key here. If it were not vectorized, it would be a scalar operation, and then we would actually see this here. And so what we've got is we're moving a packed single precision numbers into the register, and then we're doing an add packed, again single precision, and then we're moving them back out. And that's really all it is. And we know we targeted the right processor based on the assembly that we see here. So let's close this out, and then we turn off that /s, and let's turn this back down to number 1 here instead of 2, which will give us a short report, and we run it. And now we know for sure our loop was vectorized, and that the code we got was indeed for AVX. And that's all it takes.
If it's not that, I'll put out there.